Hello everyone and welcome back to Exam Ignite YouTube channel. This is Embedded System Design subject of 6 semesters, Module 3 Part 2 video, where we'll be covering the problems that are being asked in this module and also the remaining topics that we have left in the Part 1 video. So firstly, we will be starting with the preemptive scheduling. Here it is used in a system that implement preemptive multitasking. In this type of scheduling, every task present is ready in the ready queue gets a chance to execute. So the CPU time allocation for each process depends on the preemptive scheduling algorithm. So what the scheduler can temporarily stop the currently running task or process. It can select another task from the ready queue for execution. A process is moved from running state to ready state without its own request is called as preempted. The major approaches used in the preemptive scheduling are time-based preemption and priority-based preemption. Firstly, we'll be going with the preemptive SJF scheduling, that is shortest remaining time, that is SRT. It is a non-preemptive SRJ scheduling. In this, the scheduler checks the ready queue only after the completion of the current process or when the process enters wait state. But in the preemptive SJF scheduling, whenever a new process enters the ready queue, the scheduler compares its execution time with the remaining execution time of the currently executing process. So in this, the smaller execution time is selected. So then the current process is preempted and the new process gets the CPU. Hence, the preemptive SJF scheduling is also called as a shortest remaining time scheduling. So let us go through it with the help of an example. So in this example, SRT scheduling, we are having 4 processes. Consider P1, P2, P3 and P4 having a 10 milliseconds, 5 milliseconds, 7 milliseconds and 2 milliseconds. Initially, P1, P2, P3 enter the ready queue. So after 2 milliseconds, P4 will come into the queue. So now you have to check the waiting time and the TAT, average waiting time and average TAT, and you have to calculate it. So we will write it easily and we'll solve it easily. So firstly, you write down the P1, P2, P3, P4 along with the time given to it. Now what they have said in the question is they have asked you P1 to P2 and P3 is already in queue. P4 will enter after the 2 milliseconds. Now we'll start the first step. In the first step, what is the time? Time is 0. So P1 is given as 10, P2 is 5 and P3 is 7, which is the shortest among the 10, 5, 7. The shortest is 5. So what happens after 2 milliseconds? P2's remaining is what? 5 minus 2. 5 minus 2 is 3 milliseconds is remaining. And now P4 will enter. Now write down the table again. You have to put a table. I have done a rough work here. So P1, P2, P3, P4. Again here 10 remains the same. P2's was action done for 2 milliseconds. So remaining is 3 milliseconds. P3 is 7 itself and P4 will enter. Now among this 10, 3, 7, 2, which is the shortest one? The P4, that is 2 milliseconds is shortest one. So now P4 execution completes because next again 2 milliseconds it gets completes and then comes the again the shortest among this 10, 3, 7 is 3 and then the 7 and then the 2. So you have to write a Gantt chart where you have to put a single box like this. Write down in the order of execution done. First P2 was done, then P4 was done and then again P2, then P3 and then P1. So after writing the Gantt chart, you have to write down the timings in the below. So 0 to how many milliseconds did P2 take time? It took time from 0 milliseconds to 2 milliseconds. And after that, what? 2 to 4. And then after 4, add 3 to it. That becomes 7. 7 plus 7 becomes 14. 14 plus 10 becomes 24. Now this is the execution order. Now what you have to find the completion. Firstly, they have asked about the waiting time and the TAT, that is turnaround time. So first, before finding that, you have to find out the completion time. Completion time only you can write only after writing the Gantt chart. That is what firstly P1. When did the P1 process get complete? It got completed at the 24 milliseconds. So that you have to write. Similarly, P2's you should not consider the first one. You have to consider when it got completed, that executed completely, that is at 7, then P3 at 14 and P4 at 4. So now TAT, that is turnaround time, is calculated by CT minus arrival time. CT minus arrival time here is P1. It is write down the CT and arrival time. When did it arrive? Others are having 0 except the P4 because it came after 2 milliseconds. So 2, now you subtract these, you will get the TAT. And for writing the TAT, you have, and for writing the waiting time, you have to subtract TAT minus burst time. That is what TAT write down this here, and the burst time is nothing but the given time, that is 10, 5, 7 and 2. So that you have to write it down, subtract it, you will get the waiting time. To calculate the average waiting time, sum up all the waiting time, that is 14 plus 2 plus 7 plus 0, that is 23, divided by number of processes we are having is 4. You will get an average as 5.75 milliseconds, and as a turnaround time, sum up all these 4 and divided by 4, that is 47 by 4, you will get as 11.7 milliseconds. So this was all about the first problem. So next we'll move on to, that is what explained here, but in a textbook manner that I have written as a rough work and I have explained it. Next is round robin scheduling. It is a popular scheduling method used in the operating system. It is similar to round robin league format where the participants get equal opportunity. Here each process in the queue is ready and executes for a first time period. So after expiry of a time slot, CPU switches to next process. So scheduler again picks the next process from the ready queue. Now the process repeats continuously. So the features of this round robin scheduling is, every process gets equal CPU opportunity and it uses a time slice similar to the first come first serve scheduling but with the preemption. So ready queue behaves like a circular queue. So you can observe this is the round robin scheduling. Process 1, it will switch, execution will switch to 2, then 3, then 4 and again to process 1. So again here we are having one more example to understand this round robin also. Yeah, let's move on to that example. So here they have given us the process IDs of P1, P2, P3 with 642 milliseconds respectively. You need to calculate the same thing: waiting time, turnaround time, average waiting time and average turnaround time using the round robin algorithm where T is equal to 2 milliseconds they have mentioned. So first write down the table, and in the second one P1, which is which gets executed here is not the shortest one. Here it goes from P1 itself. So P1 will execute for how many milliseconds? They have given 2 milliseconds. So 6 minus 2 is 4. So from the 0 to 2 period, so P1 is executed and the remaining time is 4 milliseconds. So what is the remaining one? P2, P3 is remaining, and again P1 has to come because P1 has not got completed. Next, after this P1, what P2 will get executed? That for how many milliseconds? 2 milliseconds. That is from 2 milliseconds to 4 milliseconds period. So what is the remaining? 4 minus 2 is what? Again 2 gets remaining. So my P3, P1, again P2 will come back. Now P3. P3 is having how much? 2 milliseconds only. So for 2 milliseconds it gets completed. So P3 will be 0. What will be remaining? P1 and P2 will be P1 and P2 will be remaining. Now what P1? How much P1 was remaining? P1 was remaining was 4 milliseconds. So for 4, 2 gets executed. So remaining is 2. So P2 will come next and then again P1 has to come because it is not completed. Next, P2 will execute again in 2 milliseconds. So P2 was how much? It was 2. So 2 minus 2 is 0. Now remaining is what? Only P1. So finally P1 is 0. That gets completed. Now we have to write a grand chart like this by drawing a box. So P1 was the first we started. Then came the P2. Then came the P3. Then came again the P1, P2 and again P1. In the same order of execution you have to write. And write down the timing. This was from 0 to 2, right? From 0 to 2, then 4, 6, 8, 10 and 12. So next, completion time. What is the completion time? As I said, when did the process end? So P1 was ended at 12. You have to write down that. P2 at 10 and P3 at 6. T8 is given as CT minus AT, completion time minus arrival time. So completion time is what? As we calculated, and arrival time for all is 0. Hence we get turnaround time as 12, 10 and 6. So next is waiting time. Waiting time is TAT minus burst time. TAT is nothing but all this 12, 10, 6, and burst time is the beginning one initially given in the question, and finally subtract that, you will get the waiting time. Average of waiting time is given by the sum of the waiting time divided by number of processes, that is 3, and turnaround time is given by sum of the TATs of each process divided by number of process, that is 28 by 3, it is 9.33 milliseconds. So another one process is there, that is priority based scheduling. It is similar to the non-preemptive priority scheduling, except the switching of the execution between the tasks based on the priority what the CPU gets allotted. Okay, so let's go with the example directly. So here the IDs are given as P1, P2, P3, P4, and the time is given as 10, 5, 7, 6. And priority, again one column will be given here as 1, 3, 2, 0. And they have mentioned that 0 is having highest priority and 3 is having the lowest priority. It is reverse. And now P4 enters after the 5 milliseconds is the note they have mentioned. The first step, what we will do is we will consider the P1 because this has not entered yet. Only we have to consider this 3. In this 3, which is the highest priority is 1. So we select the highest priority 1. After 5 milliseconds, the P4 will enter with the priority 0. So what will happen? So then as the highest priority is entered now, the P1 is preempted. It is taken off and the P4 gets to the CPU immediately, which is having the highest priority will get into the CPU. After that, what? Now the P4 execution will begin. In the P4 execution, it gets completed because it is having 6 milliseconds, it gets completed. After that, next it will search for the next priority, which is the next priority now on 1, 3, 2, 1. So now it comes to the P1 and it executes for 5 milliseconds. So that P1 executes. After that, which one? It comes to the 2, that is P3, and then for the 3, that is P2. So the order of execution will be, first we started with the P1 and then it came to the after 5 seconds we got it 5 seconds remaining, then we go to the P4, gets executed, then we again came to the P1, P3 and P2. So using that order you have to write the Gantt chart. In the Gantt chart you have to write, so from 0 to 5 milliseconds it came here. After 5 milliseconds we get added to the 6 because P4 executed 6 milliseconds, so add that 6, it became 11. And similarly go on adding how much it is done. Again plus 5, that is 16, again 16, and for P3 it is 7, so 16 plus 7, 23, and 23 plus 5 is 28. Now completion time, search for the completion time here. P1 ended at 16, P2 ended at 28, and P3 ended at 23, and P4 ended at 11. So write down that TAT is nothing but was CT minus AT. The CT minus AT, in the AT first 3 are 0 and the fifth one entered arrived after the 5 milliseconds. So you have to mention that, subtract it, you will get the TAT, and in the WT you have to subtract TAT minus the burst time. Burst time is given in the question itself. Subtract it, you will get the WTs. So average of TAT is given by sum of the TATs of each process divided by number of processes, that is 73 by 4. You will get it as 18.25 milliseconds, and the waiting time is the sum of all the waiting times of each process divided by number of processes, that is 45 by 4, that is 11.25. These three questions are very important because you can expect one question among these three types, and that will be given in the question. So that completes the problem part, and next we will move on to the task communication. So in a multitasking system, multiple task process can concurrently, and each process may or may not interact with each other. So based on the degree of interaction, the processes running on an OS can be classified as cooperating process and completing process. So cooperating is nothing but the one process requires inputs from the another process to complete the execution. Competing is nothing but it does not share anything among themselves, but they compete for the system resources. So cooperation through sharing and cooperation through communication. Cooperation through sharing means sharing resources. Through communication means without sharing resources, but communication for synchronization. Next comes the shared memory. Here processors share a common memory for the communication. Information can be communicated, returned to the shared document. Other processors read data from same shared area. So this is similar to the notice board system where the information is placed in a common location and others read it. Like that, you can give an example. So concept of shared memory here is process 1 and process 2 both have a shared memory area. Fast communication between the processes is a feature, and same memory region is accessed by multiple processes. Implementation in kernel dependent, and different OS kernels use different mechanisms. Next is pipe. Here is a section of shared memory used for the communication between processes. So they follow a client server architecture. That is, process creating the pipe is pipe server, process creating two pipe is pipe client. So a pipe acts as a conduit for information flow. So types of pipe we are having is unidirectional and bidirectional. Unidirectional only one direction, bidirectional in both the directions. So the types of pipes are anonymous pipe and named pipes. Pipes that is unnamed or unidirectional. These are named, either it is unidirectional or bidirectional. Point to point communication can be seen here. Next is memory mapped objects. It is a shared memory technique used in the RTOS system. It allocates a shared memory block that can be accessed simultaneously by multiple processes. So working is a mapping object is created, physical storage is reserved and committed, and a process maps the entire memory block or part into a virtual address space. So another process maps in the same physical memory into its own address space for sharing the data. So thus multiple processes can access the same data. This is a concept of memory mapped object. So we use different functions in that. You can refer to that. Next comes message passing. It is an information exchange mechanism used in the inter-process or thread communication. It is generally an synchronous communication mechanism. Difference between the shared memory and message passing. In the shared memory, large amount of data can be shared. In the message passing, only limited information or data is exchanged through the messages. Message queue is a process wants to communicate and send its message to first in first out queue. It's called as a message queue, and its working is given here. Types are synchronous messaging and asynchronous messaging. So we are having process sends a message to the message queue, then it receives the message to the process 2. So this was all about that, and next we will move on to mailbox. So mailbox is an alternative form of a message queue used in the RTOS for the inter-process communication. So it is generally for one-way messaging. Functions as it is used for the message creation, subscription, message reading, and writing. So this is how it works. Task one, it will post a message, it will broadcast the message to the different tasks. So remote process call, RPC and sockets. It is an inter-process communication mechanism used by a process to call a procedure of another process running on the same CPU or on a different CPU connected through network. RPC is also known as the remote invocation and remote method invocation. So RPC is mainly used in the disturbed applications like the distributed applications like such as the client server systems. Technologies here used here is client and server. The types of RPC communication are synchronous and asynchronous. So features are given here. So this is the process running on the different CPUs which are networked, and here process running on the same CPU. Socket means it is a logical endpoint in two-way communication link between the two applications running on the same network. Each socket is associated with a port number which helps in delivering data to correct application. Types of internet sockets we are having is stream socket, datagram socket, and client server communication using the socket is given, the step is given here, and the socket communication where the client user uses the server host name and the port number. Client uses the client name and the port number to send the response. So communication will happen on the same CPU across the network. Socket implementation is OS kernel dependent. Task synchronization. Here we needed task synchronization to help the solution is to make it can make each process aware of the access of shared resources either directly or indirectly. So this process of avoiding the conflicts in accessing the shared resources is called as task or process synchronization. So there are many issues. First is racing. It occurs when multiple processes compete to access the manipulate the shared resource, shared data simultaneously. So there is an example of an explanation of race condition and what is the cause of that and how can we prevent that. This is an important part because a question has been asked, how do you avoid it or prevent it? Similarly, deadlock, the most important part, it occurs when the processes are unable to progress because of each process is waiting for a resource held by another process. So as a result, none of the process can continue the execution, the system will get stuck. So example, you can say process A holds resource X and waits for the resource Y. Process B holds resource Y and it waits for the X reverse. So here you can observe process A holded by resource X and wants process B, but process B is already held by resource Y and it wants process A. So this is how deadlock happens. So conditions for this deadlock is mutual exclusion. Only one process can access a resource at a time. Hold and wait. Because a process holds one resource while waiting for another resource. No resource preemption. So operating system cannot forcibly take back a resource. Circular wait. So there is a circular change for the waiting exists. So what are the deadlock handling techniques? So here firstly ignore the deadlock. OS assumes the system is deadlock free. So this method is acceptable because removing a deadlock may cost more than its occurrence. Detect and recover. So OS first detects the deadlock, then perform the recovery. It is similar to traffic jam at a junction. It has to recover it. Solve that like vehicles from one direction are moved back to allow the others pass. So similarly, OS should terminate a process or preempt a resource to break the deadlock, or else avoid deadlocks through careful resource allocating techniques, then preventing the deadlocks by breaking one or four deadlock conditions. So rules followed using that are given here. Then comes live lock. It is similar to deadlock, but the process changes the state continuously without making the progress. Starvation means it's a condition in the multitasking where a process does not get required resource for a long time. Next is integration and testing of an embedded hardware and firmware, that is software. This is an important part and the last question of this module where you can expect this because this has been asked in almost 2 to 3 papers. Integration of the hardware and software. This deals with the software into a target hardware board. This process is called as embedding intelligence to the product. What is the cause of this software embedding? Firstly, processor with internal memory, then processor without internal memory. There are two cases. So in the first case, it contains internal memory and firmware size fits into the memory. Then code is downloaded directly into the target processor or controller. If it is not there, does not support built-in code memory or the software size exceeds the supported memory size, an external EEPROM or a flash memory chip is used for storing the software. So you can observe here the out of circuit programming. Here it is performed outside the target board. So in this method, the process of memory chip is removed from the board and firmware is programmed using a device programmer. The features of that programmer is given here and the programmer is connected to the PC using the RS-232, that is USB parallel port. Then steps in out of circuit programming are given, how do they follow that, and inside in system programming, this is within the system, its requirement and working of ISP are given here. In the system programming using SPI protocol, it contains a built-in SPI interface and an on-chip EEPROM or flash memory. And also in the boot ROM ISP, it's a key feature where the factory programmed ROM memory is used that contains low-level instructions. Next is the embedded system development environment. It provides an insight into tools and steps followed in the embedded system. So you have to write this diagram without missing anything. So write down a development PC or an host. For that, we provide an integrated development environment tool, IDE tool, and an EDA tool. Along with then we send it to a target board where we interface it with an emulator PC interface using an ESP or serial or parallel, and also that emulator is connected to the target board interface using the GTAG or BDM or pin to pin socket. Also for the target board we provide an input of signal source as a function generator, and that hardware debugger interface is given to a multimeter or logic analyzer or oscilloscope. These are the hardware debugging tools. So finally, inside the CPU, there are PCB fabrication files saved. So here components, each one of them you have to explain. That is development PC, it acts as an heart of a development environment. What does it have? IDE tool means it is nothing but for coding, editing, compiling and debugging. EDA tool, it is embedded hardware design. It helps in designing the circuit, PCB design and hardware development. And the output of the generated EDA tool can create a PCB fabrication files. Then emulator hardware, it is used for debugging the target board. It creates a communication interface between our PC and the target board. We use a different interfaces to link them. Signal source is given by the function generator. Target board is a hardware platform that we use. Then hardware debugging tools are also used, that is digital CRO or multimeter or logic analyzer. Then tool selections are done by the IDA and the EDA tools are selected based on the target hardware development that is required. So we are having different types. There are also two development tools, freeware tools and license tools. So this is an important question. You need to write the diagram and ask. This is a model question paper question also. With the block diagram, you have to explain it. So this completes the module 3 part 3 video. Part 2 video. I hope you have understood everything. Please do like, share and subscribe to Exam Ignite. Thank you for watching.